Hello, 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 hello. I haven't done a Grasshopper tutorial in a while, so I just wanted to catch up and make a few parametric walls. But there's a twist. There's a twist to what we're going to be doing. At the end of these videos, hopefully more than one, I will be ordering the designs that I make to be CNC milled, or at least portions of the designs. And we will be able to see, what we get in an actual kind of physical form, me holding it. So if you're interested in that, just quickly skip ahead and then skip back to the start of the video. Anyway, I guess we can get started with wall number 1. And for this, I will probably, since it's our first one after a little bit of a break, let's start with a Voronoi design, because that's what you do. Immediately jump to Voronoi. So I guess the first thing that we need to do is define how big the wall is going to be. And I will go for something pretty small at the start, like 3 meters by 2 meters, something like that. So we can either define it here in Rhino or we can do that in Grasshopper. I always prefer to use Rhino, like just drawing out a curve in Rhino. And I'm just going to type in 3000, a rectangle, 3000 by 2000. And then just selecting it and typing in ZS to zoom selected, enter. And now we have the rectangle centered in our view. And this is like 3 meters by 2 meters. So I prefer having it in Rhino just because it's going to be so much visually, I don't know, visually it's easier for me to change the proportions, even though I could just change the numbers, in a rectangle node here in Grasshopper. Either way, let's reference this in. So I'll just create a curve component in Grasshopper. Curve. Oh, and I should use, as per usual, bifocals curve component. Right click on it, set one curve, select the rectangle, and then you have them referenced in, linked, right? So for now, actually, I'll just keep it. For now, we will be working in Grasshopper for most of the time. So how do we want to do this? Well, we will be using, as I said, we will be using Voronoi. So let's just type in Voronoi. There's Voronoi 3D and Voronoi. I will be using the regular one, the 2D version, Voronoi. There we go. It asks us of points, radius, boundary, and what plane should it generate the cells in. So let's just get some points inside of this curve. And this curve, since it's a rectangle, can be regarded as a region, meaning that I can just say populate 2D, hit enter, connect the curve as my region input, and it's automatically going to populate it with 100 points. Because that's the n input, the count input is by default 100. If you want more, you can just, let's say, create a number slider, type in 200. So it basically, when you type in 200, it creates a number slider that's, locked at 200, and its minimum is going to be 0 and maximum is going to be 1000. If you want a more specific slider, let's say one that starts from 100 and ends at, let's say, 900, then the shortcut for it is 100 ... 900. Enter. Then you will have a slider with a specific range. So that ... basically says that you're specifying the minimum and maximum range of the slider. So we could use that as well. Let me just connect that to the N. You can see how this works, right? So for now, for testing, just so that we don't crash anything, I'll use like 150 points. Let's say 150. Why not? Right? And let's just connect those points to our Voronoi point input, just like that. All right, you can see that our Voronoi cells are created, but the problem is that it reaches over or spills out of our wall boundary, and we need to fix that. And it's actually a very simple fix. It's the boundary here, the B input for the Voronoi cells. So I'm just going to connect my curve to the B input like that. And that's it. Now we have ourselves some Voronoi cells. So from here on out, I kind of want to start messing about with these cells, or maybe we should first, give me a second. Do we first create a wall? Do we first create a mesh, or do we first mess with the cells? I guess we can first create a mesh, just the mesh topology. That's going to be actually pretty simple and pretty easy to do. So let's say we have all of these cells. Oops, sorry, that was my bad. Back to perspective view. Each of these are closed polylines. If I were to bake this out real quick so that I can select them, you can see that these are like separate closed polylines, right? By the way, quick bake is the insert key on your keyboards when you have a node highlighted. So instead, what we can do, then we can scale them, right? Let's say we take the cells and we scale them to the center points, just like that. And we scale them with a factor of, let's say, 0.6. So now we can control it. We can control the inner, let's say, diameter of the cells. It's not a diameter, but you get what I mean. All right, so we have that. What of it? I kind of want to have, so I want to create a mesh for every cell, and I want the mesh to dip down. Yeah. To basically create, like, every Voronoi cell needs to be like a bowl shape. So our scaled versions need to be able to move down. And also I really want every cell to be its own little branch. So what we're going to do is I am going to graft the populate 2D node, the output of it. I'm going to graft this and connect that to the C. It immediately kind of makes a weird thing. Don't worry. This is because every populate 2D point from graph tree here comes as a separate branch. Think of it as like many separate lists of one point in each list. While here, the Voronoi cells are still one list with 150 cells or polylines. So I'm just going to right-click on the C output here and choose graft here. Right-click, graft, and now it's the same thing. Except that in this case, when you graft, when you have both of these inputs grafted here, the scale actually, now the output of it is for each individual branch, and that is going to be quite necessary later on when we will be dealing with specific smoothing or rather subdivision. I'm planning a few steps ahead in this case. Let's move these inner cells down, so it's gonna be negative. It's gonna be Z, unit Z. Let's move them down by like, well, that's the question. What's the material that we're going to be using? You know, what's the deepest that we can go? I'm thinking 18 millimeter MDF board. So the deepest that we can go is 18 millimeters, but I kind of want some breathing room. So let's just say 9 millimeters for now. So we just move these rectangles down by 9 millimeters. Okay, great. So now we have our cells here, and we have our moved center cells. So technically I could just loft between them like that and like that, and this should work, yeah? So just kind of lofts, right? Easy. But you can see that loft took like 1/3 of a second, and as we will be increasing the count, this will become heavier and heavier. So I'm not sure if we should be using loft. Perhaps we should. Sorry, give me a second. I'm thinking. Well, technically we can use loft. Let me just double check how fast or how slow is it gonna get when we use count 500. 1.2 seconds. Oh, that's not that bad. Let me show you a faster way though. Or should I? Yeah, I should. Pedagogical. So instead of instead of using loft, what you can do is you can explode the Voronoi cells, the starting polylines, and you can explode the scaled down, moved down polylines. And let me just disable preview of all of this because it's a little bit in the way. And we can keep that. And here you will have the vertices, right? Here and here. And you can merge these vertices into one list like that. And since the data branches are matching up, that's why we graphed, by the way. Once you merge, you have all of the vertices in one list for each cell. So like this cell, all of the points here are in one list, and for this cell, all points here are in one list, and so on, right? So what we can do with it, we can use a Deloney mesh right here. Connect that. Oh, and I need to display preview mesh edges so that you can see the mesh edges. And now we can see it makes a mesh for us. And this seems to be a little bit icky. I mean, hey, it works, but I don't know. I don't really like it. So I think for this, we will be using loft between the Voronoi cells and the scaled down moved versions of the Voronoi cells, like that. I should really use merge here. Yeah. I should do it this way, just for clarity and for it, you know, to look clean. So we get this, and we just need to fill in the bottom, I guess. So the bottom should probably be filled in with some sort of a... We can either triangulate it, that might work, or we could just use Deloney for the bottom, because we don't really care. We only care about this being as clean as possible. Yeah, let's use Deloney mesh. So what do we mesh? Well, we take these inner perimeters and we explode them as we did before. And I'm also gonna take I think we should take like the center points here as well for these perimeters, because I kind of want like a point right in the middle, probably. Yeah, I do. So there's this graphed tree gives us exactly that. As from populate to D, we graphed the points and we get those here. So I will just use merge to get the center points and to get all of the vertices from these curves here. So all of them are in one big happy family here, one big happy family here, and so on. And let's just see. Oh, but if you check with your mouse, if you hover over the merge output, you see that they're not actually in a happy family because the addresses for the data tree, like branch addresses, they don't match up. And this is what Grasshopper does all the time, and I absolutely hate it. But fixing it is actually very simple. You just right-click on the D1 and D2 inputs, and you choose to simplify, just like that. And now everything matches up and everything's nice. I don't know, everyone's complaining, but for some reason, McNeil just decides that, oh, no, we don't need to fix that. Anyway, let's create a Delaunay mesh right here. Bada bing, bada boom. We have ourselves a mesh. Okay. So here we have a loft and here we have a mesh. So we need this loft to become a mesh, right? The nice thing about this is that since we are taking the polyline and we're scaling it down and we're lofting, we're sure that every segment of the loft is a quad, has 4 corner points, meaning that I can just use simple mesh component, connect it, and it just works. By the way, simple mesh, I don't remember if it doesn't come together with Grasshopper by default, you can find it either in mesh edit tools or mesh edit or input for Rhino or somewhere else. Mesh plus maybe, but it might be just coming in together with Grasshopper by default. I don't remember. Anyway, we have a mesh here. We have our mesh here. We need to merge these bad boys into one big happy family again. Guess what? The family is not happy. So what we do, we simplify as per usual. Now they do see each other and they get together in one list. And then do we just mesh join? I think we can just mesh join. Just like that. Let's hide everything. Let's take a look at our topology. Looks really, really bad, but don't you worry. We will make it even worse. So for now, we have ourselves 150 meshes. Well, that's expected from 150 starting points, right? So now it's the time to actually smooth out each mesh individually, each cell. So I will just use Catmull Clark. And by smooth out, I don't subdivide. And Catmull Clark, this always happens. Catmull Clark gives us an error saying, well, multiple errors saying 2 consecutive edges, 1 and 0 have the same value, blah, 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 blah. If you get that message, a trick that I usually use is I use combine and clean, just like that. And I use deconstruct mesh. So combine and clean removes all of the duplicate unnecessary points. The construct mesh kind of explodes everything into point and face information lists, and then construct mesh reconstructs everything, but this time without the points, without the duplicate points, right? Because combine and clean just remove them. Why does combine and clean keep the face information? I don't know, but this kind of workflow for cleaning up seems to do the trick, because now the Catmull Clark is not complaining anymore, right? Instead, construct mesh is complaining, invalid mesh face encountered, but it just skips over it, and we're happy with that. So we get ourselves a smoothed out version right here. How do we fix the gaps? Well, the gaps are actually here. Smooth naked edges. You can see 0 is fixed, 1 is smooth, 2 is corner fixed. So if I just type in //0, hit enter, and plug that into S, or you can just use a slider, by the way, and just 0 slider. That works as well. But if you plug it in, it will lock the corners. It won't let the corners run away. And instead, you will end up having a pretty clean, not clean, but like a topology that works. And let me make this a little bit more aggressive, because you probably can't see what the hell we're doing. So instead of 9 millimeters for moving downwards, I will move it down by like 25 millimeters just for a second here, just like that. And let's jump to shaded view so that it's a little bit more glossy. See, it's like a crater system thing going on. What's up with the points? Didn't we move the points down? Oh, my bad. So the points, these guys, the center points, they also need to be moved down. And I didn't do that. So for the move, I will just copy the move component here, where we moved the scaled polylines. I'm just copying it. And the grafted points, I will move them down as well, just like that. By the same amount, by the way. Right? So now the craters are actually like properly craters. All right. We have that going on. And it's not that slow. I mean, the loft is really killing it in terms of how much of a bottleneck it is. But it's reasonable. It's fine. It's going to be fine. All right, so we have ourselves a Catmull Clark subdivision, like first level Catmull Clark subdivision here. Then I will just join everything. Mesh join. Make sure that your output or input for mesh join is flattened so that all of the meshes see each other and are able to join. They're not in separate branches. And then let's use Catmull Clark yet again, I think. Well, let's just clean everything up. You can't have enough combine and clean. I mean, there's never enough combine and clean nodes in a definition. There's also unify mesh normals or mesh unify normals. That also helps with making sure that all of the faces are looking upwards. And then I will run a Catmull Clark subdivision. I guess we could run it at level 2, but I don't think at this stage it's necessary. So I'm gonna run it at level 1. And smooth naked edges, well, it's just how does it treat the corners, right? When we have smooth naked edges set to smooth, basically the corners are gonna be rounded. So instead, I'm just gonna change this to fixed, and I don't remember which number, what was it? It was 0. Or I can use corner fixed. Yeah, sure, let's use corner fixed. So I'm just gonna say //2, enter. Connect there. That didn't help, sure. So then instead of 2, we will use 0 to force a connection there. There we go. All is good. So we have ourselves a little bit of a kind of Voronoi crater system going on. Let's create a custom preview so that it's pretty. With a color swatch set to like gray-ish. Oops, yep. Just like that, perfect. Okay, so now we have, once we have this, it's time to introduce some complexity, I guess, to the system. Let's start grouping things because it's getting a little bit out of hand. So this is, this group is smooth. So it's used for smoothing things. Then this group is for cleanup. Then this is a little bit tricky. We will need to fix those groups once we introduce more to this, because this is gonna get messier than it is right now. I'm sorry, but it is what it is. All right, let's introduce an attractor curve to our scene. I will just draw any random curve that, well, actually, let's just do a walk. Something like that. You know, just a curve. Reference it in. Right click, set one curve. There we go. It's right there. And then I will, well, then this is where we start messing around. Populate 2D, huh? What if the further the points are from this curve, the more likely they are to be removed? So basically the points that are curve controls the density of the points, if that makes sense. So if we have populate 2D, I can use pull point component here, and I can pull these points onto this curve to get the distances, right? And I can take these distances and I can sort them from smallest to highest. And together with the distances, I can sort the points. So from now on, the output of A, the output that I get here, is going to be a point that is closest to the curve is going to be at the top of the list, and the point that is furthest away, let's say this guy right here, a point that is furthest away from the curve is going to be at the end of the list. So it's sorted. Then I can also, by the way, if you hold down the Alt key and you just click and drag, you can make some space in your definition. Okay, so if I have this list of points, I can partition this list into segments, into separate segments. And I can measure the list length, for instance. You know, I can ask how many points do I have? Or I could just use the slider as well, that works too. Actually, whatever. List length. It's gonna give us a shorter wire, so I'm just using that. And I can say, well, what's the size of the partitions? That should be like list length divided by a number of how many partitions do I want. Let's say I want 3, just like that, and connect it there. So I have now 3 separate lists, or 3 branches, 3 data branches with 50 points in each branch. First branch is the first 50 closest points. Then I have the in between 50 points, and I have the 50 furthest away points. Okay, great. Now I need these points to be deleted, removed. Well, the ones that are closest should not be, nothing should be removed from them, but the ones that are furthest away should be, let's say, completely removed. So how do we deal with that? Well, I can use random reduce, which asks me of a list. So I give it 3 lists in this case. It asks me for how many items do I want to remove. And that is going to be tricky. So I need like tree statistics component to tell me how many items, first of all, there are in each branch. And there's like, in this case, since we're dealing with 150 and it divides by 3 very cleanly, we have 50. So it's easy. But if we had like, let's do 149, right? Then it doesn't divide cleanly, and it's going to be 50, 50, 49, right? It's going to have like different amount of points in each branch. So for tree statistics, I get the length here, and I will need to multiply the length by some amount, or rather by 3 amounts. And each, and let me just graph this, because I can see from the dashed line that here the information that comes in is graphed. So I'm just graphing this as well. That should work. Yeah. And then the question is, well, what's the multiplication? What's the number that we use? And for that, I will use a range, a number range going between 0 and 1. So if you multiply, should it be other way around? Give me a second. No, it shouldn't. It should be fine. So the range basically gives us numbers, right? In a given range. And by default, it's between 0 and 1, just like that. So we just need to control how many numbers do we need. And we can do that by just measuring the count. But the problem is that if you just plug in count to the n input here, you get 4 numbers instead of 3, even though here it says 3. And that's because it basically divides up the range. It doesn't extract 3 numbers. It gives you like 3 portions. So since there's a start and the end of the range, there's like always +1. So what you can do is you can just right click on the range n input here, choose expression, and here you just type in x minus 1. Is it minus? Yes, it's minus, x minus 1. And basically any number that you give it is going to be 1 less. So now it's 0, 0.51. So now, how does this work? Well, random reduce gets 3 lists, 50, 50, 49, and it asks how many, here it asks how many numbers or how many points should I remove. And in this case, we can see that with the range, we can see that, well, take the maximum amount, and for the points that are closest to the curve, multiply that by 0. And basically it's going to spit out here 0. So don't remove anything. Then for the, let's say the second range, what? Give me a second. For the second group, the in-between group, it just says, well, multiply it by half. So remove half, right? And the third group, the furthest away, remove it all. So whatever the maximum number is, multiply that by 1, and that's how much you should remove. This is how it works. So now these randomly reduced points can be used for our Voronoi cells, for instance. I will just right-click and flatten the output to just have them all in one list. And I'll do the Alt key trick, Alt and drag, to just make some room for myself. But basically this random reduce now can be used instead of the regular populate 2D. Just like that. And I'll just plug it into my Voronoi input here and plug that one into Graph. So wherever I had populate 2D plugged in, I instead plugged in the random reduce node. All right. So this is gonna be, let's just group this. And let's just call it control density. All right, how does this look like in a perspective view? Oh, and we don't want to see the points. I mean, not that bad. Not that bad. Could be better, but hey, if it works, it works. Like I like the weird ass bend here. Why is it happening? Anyway. Doesn't matter, we will fix that later. For now, this seems to work. So now I'm going to change the amount of like these steps that I measure. So instead of 3 steps for partition list, I will use like 6, something like that. I could use even more, but I think 6 should be enough. Or maybe let's just do 10, whatever. 10, and then we can increase the count to something like 250. There we go. So we have this. Then let's control how much does it dip down, right? We kind of want to control that as well. So from our brand new points, right here, from our brand new points, I will just measure the distances that, how close they are to the curve, because the curve should also influence how deep do they dip down, right? So I will just say pull, again, pull point, just like that. Pull point, and our curve that pulls is indeed our control curve right here, or our attractor curve right here, and basically we get the distances again. And this is like the most basic thing ever that we always use, so I will not be diving too deep into it. We will use remap numbers, we will use graph mapper, and we will use remap numbers as again. Okay, first remap numbers takes all of the distances and asks for what's the largest and the smallest distance with bounds, and remaps all of them to be in between 0 and 1. So the largest distance becomes 1, the smallest distance becomes 0. Then the graph mapper can eat it quite easily, because graph mapper works in a range between 0 and 1. And let's just create a curve, something like this. By the way, right click on the graph mapper, graph types, Bezier curve. And then you can play around with the nice control points here. So do something like that. Then the spit output here for the remap numbers, the last remap numbers, is going to be the second remap will take ranges between 0 and 1, numbers between 0 and 1, and will remap them to actual movement values that we use here for negative unit z. So I'm just going to say, let's construct a domain, construct domain, like that. And let's just say the maximum, as it gets, wait, the closer it gets, the closer to 0 it is. So as it gets close, let's just say as it gets close, it moves up by 9 millimeters, like that. And as it gets further out, it moves down by 9 millimeters, so just negative. Other way around, sorry. It moves down the closer it gets to the curve, and it moves up the further it is away from the curve. What am I saying? And then we get these numbers, and we, instead of just a static value here that we had, right? We will feed in these numbers here. I think I just crashed it. We can't just do that. By the way, just hit escape and hold escape, and it's not gonna crash for you. I forgot that we need to actually graft. We need to actually graft the output for this to work. So I'll just right click, remap numbers, output, and I'll choose to graft it like that. Connect, and now it works just fine. And you can see here, we have some hills here, right? And we have some divots, like some valleys here. So we're getting there. We're getting there. Let's hide a few things. Let's bake this out. I kind of want to see it in Rhino at this point. And the thing that I like to use is called emap. And let's just find like a, it should be an Arctic view, right? Yeah, Arctic view doesn't show the mesh edges, so I can more easily see the actual form. Yeah, that seems to be okay. That looks fine. Yeah, sure. So I'm happy with this, so we can move on. We can continue. I kind of want let's think. Okay, so I kind of want the inner cells to be a little bit more complex, what's happening inside of the cells. And also, like the top surface right now, it's very clean. It's very, like all of these edges of the cells are always in the same height. So I really want to mess that up. And it has something to do with this Voronoi. So what would happen if we explode each Voronoi cell like that? So we get the vertices. And let's just simplify this so that our data structure is clean. So we explode the Voronoi cells, we get the vertices, we deconstruct the vertices to get their X and Y position. And I will use the X and Y position because all of these points are duplicate, right? So I need to move both duplicate points in the same height. So this is how I do it. I deconstruct the X and Y position and I will graft both of these so that they're kind of separated for each point. And I'll just add them up into one number. Let's just add. Okay, so this is like just a random number, but every point or every pair of points that are in the same place share the same number. This is very important. Okay, so with that in mind, I can create a random number, and the random number is gonna be by how high do we move these points. So I will just create a / and I'll just type in 0 to 9. So somewhere between 0 and 9 millimeters, just like that. And then I will just simply say that the seed value is from my, like it's the number that was generated for each point, that addition output, like that. So this is us taking into consideration that random in Grasshopper is not actually random, it's pseudo-random, and we're using the seeds to our advantage. It's actually pretty, yeah, that's, I don't do that often. Okay, let's clean this up again, simplify the output. Let's trim tree. Basically, we want to, right now, every single point on every single cell had its own little branch. So what we want is we want to regroup all of these points. So we're essentially what we're doing is we're getting rid of these two grafts by using the trim tree, right? We're merging back the branches. So with that done, I can just say that it should be, each point should be moved, I think like that, in Z value, along the Z axis. Missed it. There we go, along the Z axis. And after these points were moved, and you can see that each of them were moved, we can construct a polyline. Polyline, yay. And now, this whole thing, we just group it and we say distort each cell upwards. Oh, close enough. So now these are not flat anymore, they're actually distorted, and you can control by how much they're distorted in here. So right now it's from 0 to 9, but I can say from -3, I don't know, to 9, something like that. So it sinks down as well. And we can just use, instead of this Voronoi, these Voronoi cells, we can use the distorted ones. No, we can't. It just freaked out. Why? Oh, that's because this is clean, like remember the not being a big happy family? They're not being big happy family. So we right-click, simplify, we right-click, simplify, and now they're happy again. Okay. So now there's a little bit of distortion going on. I'm happy. I need to... I hate it when wires go backwards and forward again, so I'm just cleaning it up a bit. All right. Now, how do we make this even nicer? Well, I could say, let's scale again. Scale this again with the same center point that we used for the other scale. here. But this time the factor, let's say, is 0.85. Here it's 0.6, and here it's 0.85. So we get all of these cells here. And with these cells, I could just say, actually, I don't really need to. Give me a second. Yeah, actually, I don't really need to do anything more with these cells. I just need to create an additional loft. So instead of, when these lofts are made, right, I will just say that these lofts should be made between these two, like that. And we will fix it in just a second. But basically, between the full perimeter, it lofts to 0. Actually, let's hide all of that and just look at the loft, like that. So it lofts between the full perimeter that was distorted between this polyline, and lofts with this polyline right here. And then I just need to create one more of these, right? So there's gonna be, I'm just gonna copy and paste just like that. And let's just choose to disconnect, like that. Disconnect, like that. There we go. So then we need a loft between this scaled polyline right here and this scaled and moved polyline right here, right? So I will just feed them in to D1, and this one goes to D2. Just like that. We get ourselves the second ring in here. And then this needs to be added in, and I'll just create. Once you zoom into the merge component, you can see that plus and minus signs appear. This is how you add additional inputs. So where we have like the final merge before we do mesh join, I'll just zoom into that and click the plus sign. We have D2, we need to simplify it, plug in our new loft, and that's it. That should work. Let's hide all of this and let's take a gander at our custom preview. Yeah, works like a charm. All right. What else do we want to do? Let me experiment a little bit. Yeah, that is gonna look nicer. Okay, so you can see here, for instance, this area, it's a little bit on the soft side, right? But if for the first Catmull-Clark subdivision, if I, instead of using level 1, if I use level 2, come on, level 2, it sharpens it up quite a bit. So it makes everything a little bit more technical, so to say. Might not be your style, just something that something that you can control. So I'm telling you, telling you that. Let's take a look at it with the Arctic view. Pretty soft, pretty nice. Definitely not gonna be that soft once it's baked out. Instead, let's just let's group this, call it outer ring. Because it is. Call this mid ring. And the Delaunay mesh, this one is gonna be bottom of the well. That is not how you write well. Doesn't matter. Or is it? Maybe it is how you write well. I don't remember. Anyway, bottom of the well is basically the cap on the bottom of the well. So let's bake this out. Let's take a look at what we have here. Are we happy with this? Definitely not Arctic view. Have my Evangelion red here. Yeah, that's not that bad, honestly. And that's pretty sharp, and then whatnot. Yeah, I dig this. We can work with this for sure. Okay, so let's now make it much more complex. And the way you do it is by just increasing the number at the start, of course. So instead of 250, let's use 750 and just give it a second because the lofts are not actually not that bad. So we have ourselves a little bit of a resolution thing going on, like higher resolution thing going on. Seems to work just fine. Okay. For now, I will say that this is a good enough of a pattern. It's a little bit messy there, but sure. All right. Let's bake this out. Move this out like that. Oops, not export. That was my bad. Emap. Let's use emap to check some things. Not arches, fluorescent tube. Yeah, honestly, it's seems to be just fine. Okay, I just noticed that my camera died. Doesn't matter. I will figure it out later. For now, this is where we finish up with the grasshopper part. So if you were just here for the grasshopper, we're done. But I will be changing a few things. So first things first, 500 by 500 millimeters, huh? Let's try that out. There we go, something like that. And let's just find an area which is interesting, so that we can get like best of both worlds. Not both worlds, but you know what I mean. Perhaps something here. Yeah, something like there. And then I'm just going to take this and use it to split mesh, or mesh split, sorry. With this little rectangle here. It's gonna take a little bit of time. There we go. Well, I have it in Grasshopper, so I'm just gonna delete this. And this is our little part that we're gonna test out for this full wall. And let's just do a few tricks here. So to send this to I could just send it over as it is to the CNC operator, and it would work. But just to be on the safe side, I will make a copy of this. I will quad remesh it. I will use quad remesh to remesh it. Target quad count, let's do like 5,000. Convert to sub-D, yes please. Detect hard edges, yes please. Delete input objects and sub-D corners. All of these are have to be selected. I just said okay. wait for it to calculate. There we go. Let's just double check in Evangelion Red. Doesn't seem like we're losing too much information. We're losing a little bit here compared to here, a little bit of sharpness. So I'm just going to actually go back. So I Control Z, and I will quad remesh with slightly different settings. So detect hard edges, yes. Convert to sub D, yes. Delete input objects, yes. Sub D corners, yes. Target quad count, 5000 seems to be okay, but I'll just change the adaptive size to 100% so that it is able to add polygons where it needs to, right? So where the polygons are most needed. And it still doesn't add that many polygons here. That is very strange. Because it seems to be quite a sharp area there. Maybe it's just a visual thing. Let's do emap to test it. Arches. Actually, with the emap, I can really tell that it's pretty sharp. Well, actually not as sharp as there. Doesn't matter. Let's move on. This is a tutorial. Let's move on. Okay, so now as I have this sub D, I can actually create a NURBS surface from it. So I'm just gonna type in 2 NURBS and just hit enter and wait for the magic to happen. This is quite intense in terms of computation, but you know, a laptop handled it. So I assume if your computer is not a full blast potato, then it's gonna work. So now this is a poly surface, which means I can duplicate the border, and I can move the border down, scale it, or actually let's do it properly. I'm sorry. Let's just select this bounding box, create a bounding box for it. Let's measure the distance between the top and the bottom of the bounding box. And the distance is almost 16 millimeters, which is great. That means we have a little bit of space because our material is going to be 18 millimeters. So I'll just scale 1D between this and this point. I'll just type in 18, right? Because that is actually the actual thickness of the material that I'm gonna have. And then I will select the bottom surface. And by the way, to select it, I just use Control Shift and click. Control Shift click. And I'll just type in extract SRF. So it just kind of gives me that surface, it extracts it. I don't need the top of the bounding box, so I'm just going to delete it. I will just be using this extracted surface. So now I have, and I also need to select it and type in duplicate border to get the outer perimeter of it. So now I have the top perimeter here with the duplicate border. I have the bottom perimeter here. Guess what do? Just loft. I loft between them. And you can see that the loft is absolutely disgusting, right? And that happens when ISO curves, when it can't really match up that well. That the ISO curves don't match up between the two surfaces. So if that happens, what you can do is you can just, instead of just trying to loft it that way, you can scale up the bottom surface, so that is a little bit bigger. Take the top curve and project, not to C-plane, but just project it to the surface, to the bottom surface here. and you get this kind of nice rectangle, and now we don't need the surface anymore. And the reason why we do it this way is because now the control points will match up, because what it did is it just took the top curve and it just projected all of its control points down. So now if I loft, you can see that all of the perimeter is quite clean. I just delete the curves, select all of this, type in join, and to get the bottom, I just type in cap, because it's flat, so it's easy. And now this is a closed poly surface. So I'm not sure if the CNC operator would like me to send over a closed poly surface or a mesh. But you can never be too sure about these things. If I were to look at them with my Evangelion Red preview, you can see that both are quite similar. Of course, this being like 100 times more computationally expensive than the mesh, but hey, we do what we must. All right, so now this is where it gets interesting. This is me pausing the project or the video for, well, for you it's gonna be a few seconds. For me, it's gonna take a little bit of time, and CNC milling it out. Also, just if I forget to say it later, all of the files available for Patreon supporters. So if you're lazy and you don't want to follow along this long-ass tutorial, but you still want the files, consider supporting the channel. Link in the video description. Okay, now it's time for some movie magic and a cut to the future. All right, we're back. We're back. So, yeah. Here it is. Let me try and catch some light with this. You can see it's quite organic. It's quite nice, honestly. And the quality is really good as well. It took an hour to CNC mill, so it's a pretty kind of the drill bit that was used is pretty fine. And the step size is pretty fine, but it's worth it, I think. So here's the pattern. We're gonna make many more just like these in the future tutorials. Hope you enjoyed this one, and I will see you in the next one. Later.